people, here I am once again recording for you. I want to make a video review on the semi-exam, on the second part of the semi-exam. I pretty much saw that in the first part of the semi-exam, most of you did it actually well, and it wasn't hard actually. So most of you deal with it pretty good, and I want to focus on the second part because certainly those problems are way more challenging, and I want to give you some advices and things on how to approach this kind of problems. So here's the first one. Let's read it. It says, we observe that the highest point of a tower with an angle of 72 degrees over the horizontal. If we get away 350 meters, we saw it with an angle of 31 degrees. What is the height of the tower? Well, no one, pretty much no one gets a problem from the first reading. So the first thing is, don't get nervous, don't get like afraid from this kind of problems, because if you read it with attention and slowly, you can actually get a picture of it in your head. I on purpose didn't attach a picture of this problem because I want to see how you manage to make a picture of it, to make a sketch, to make a draw, okay? Because it's a very important part of these kind of problems, how to approach by making a picture. So it's an application problem, and it can be abstract to a math problem, of course. So in the first part, just in the beginning, we can actually make a picture. Just check. We observe the highest point of a tower with an angle of 72 degrees. 70, yes, 72 degrees over the horizontal. So you go to your space, your tucked space, and you can put a line here, and this is like the ground, yes, and here you are. Here you are. Yes, very good. Um, the problem just says 72 degrees over the horizontal, so you can pretty much just assume that the horizontal is the ground, because the problem is not saying anything else, like, oh yes, an horizontal over 1 meter over the ground or something. So you can pretty much go straight forward and assume that the horizontal is just the ground, and you are seeing a tower, just something like that, just a tower, and you are seeing the highest point of a tower, the highest point, like this. This is the horizontal, so this is the highest point, and you are seeing the highest point with an angle, just check the angle of 72 degrees, yes? An angle over the horizontal, just like that. So we pretty much have a first approach, a first draw of it. It's very helpful to do it. And what is this next? If we get away 350 meters, we saw it with an angle of 31 degrees. What is the height of the tower? Okay, if we get away, well, if the tower is here, getting away is go that way, yes? And it makes sense, because if we continue the draw and now put yourselves here, and this is still the horizontal, so you're seeing the highest point of the tower. You now have angle less than this one, because you are getting away, so the angle is getting smaller. Can you see? So let me put it straight, more straight. Yes, the angle is getting smaller. If you were moving towards this direction, the angle will be getting larger. So you can see that you are going to this direction because the angle is getting smaller, and it makes sense because it's getting away, not getting closer to the tower. So this is 31 degrees. Now you have a very good sketch of the problem, and you can translate this picture to a mathematical problem. And this is like the sketch of the problem, a sketch of the problem, of the problem, of the problem. And from this sketch of the problem, you can get an abstraction of the problem. What is this abstraction? Well, we take the mathematical concepts, the mathematical objects from this sketch, and make a mathematical problem of it. Something like this. And like this. Can you see it? Maybe my draw is not better. I'm missing some details. But you pretty much get it, don't you? So the problem says you're getting a weight 350 meters. So obviously it's not scaled, but these are 350 meters. So this distance from here to here, it's 350 meters. Well, when you make the abstractions, you no longer have to say meters or kilometers as long as you take all the distances or all the magnitudes in the same units. You no longer have to say meters or centimeters or seconds or whatever when you make the abstraction of a problem. Okay, so this is the abstraction, and this is 72 degrees, and this is 31 degrees. Now that you have the right picture, man, you have make like 50% of the problem. Now that you have the right picture, okay? So basically you have to find x. Yes, this side is x, and this let's call this point A and this point B. So you know that the distance from A to B is 350. Yes, basically. Now you have information about this side. Oh my god. About this side, and you have information. Well, you want to know this other side. You are actually not very much interested in what should be the hypotenuse. By the way, I didn't mention it, but since this is a tower, you know that buildings are built with an angle of 90 degrees. Yes, so this is actually a right angle, and since this is a right angle, this is a right triangle. Okay, so you have two right triangles, this right triangle and this other right triangle. Okay, so this is the information we have, and as I was saying, you don't have to deal with the hypotenuse. The hypotenuse is actually something you are not very interested in, and you don't have information about the hypotenuse. So since you don't have information about the hypotenuse and you are not interested in the hypotenuse, don't move the problem in a way that you have to use the hypotenuse. Okay, so this is a problem involving angles and sides. So using trigonometric radius is actually very helpful. Okay, it's something you have to start thinking. Once you know, you have to solve for sides and angles. Okay, if this was only sides, maybe Pythagorean theorem will be an approach, but since we have information about angles and sides and missing sides, trigonometric functions and trigonometric radius are a very straightforward kind of problem. Okay, so we don't have the hypotenuse, we are thinking in trigonometric functions. So what kind of trigonometric function doesn't involve the hypotenuse? Think of it. For example, the sine involves one of the legs and hypotenuse. The cosine involves one of the legs and the hypotenuse. The tangent involves only legs. So you have your answer there. The tangent involves only legs. So if we, for example, let's focus on this triangle. Let's focus on this triangle up here. If we want to know the tangent of 72 degrees, this is equal to, you know pretty well, this is equal to the leg, the opposite leg over the adjacent leg. Okay, so which side is opposite to 72 degrees? Opposite. This is the X. Yes, and which is adjacent? This. Let's call this point C. So from B to C is the adjacent. From B to C. Okay. Excellent. And now let's focus on this other triangle. Okay. This is the bigger one. Now, if you want to know the tangent of 31 degrees, it's equal to the opposite leg over the adjacent leg. So the opposite leg to this 31 degrees is the opposite x. Yes, x over, which is the adjacent leg to 31 degrees. Adjacent is all this. So basically is it 350 meters over BC plus this plus this is all this side. So this is the adjacent side to the angle of 31 degrees. So it's basically 350 plus BC. So we have two questions to deal with. Okay, and the video is getting a little bit longer, so I will need a second part. I will make a second part. So if you're having trouble so far, let's put it in the comments. Tell me, because in the second part we are going to solve this. Okay.